Hi, this is a quick introduction to Variational Monte Carlo for our Capstone team. So, first of all, I'm going to try to sell the Variational Monte Carlo. It is probably useful when you're putting together your final presentation too. So, VMC is basically a very slow, which is a bad thing, method for computing the ground state energy of a molecular system. But while it's very slow and the computing time increases exponentially as the systems get bigger, at the same time it's also parallelizable. The reason being that Variational Monte Carlo is a Monte Carlo algorithm, and you can essentially have multiple samplers performing Monte Carlo sampling, and as a result, as many samplers as you have, you can basically increase the speed of computing the integral, which is essentially what most of the Monte Carlo systems do, either that or optimizing something. So while it's very slow, it's also parallelizable. That's a good thing. In terms of the exponential increase, that's not something that is particularly the problem of VMC. Any other quantum mechanical algorithm has that problem as well. So that's kind of not our problem here. The other problem it has is the negative sign problem, which basically has to do with the limitations of a floating point variable. But we don't care about those. What we care about is that it performs no approximation to many-body interactions. In other words, it's taking care of those interactions in the exact manner. So in a way, VMC is a very, very accurate method. And that's why it has to become more available for people who want to perform quantum chemistry calculations that are important to be done exact. So before we jump in, I just want to remind you what a wave function is. A wave function is this entity, in other words, that basically allows you to measure the probability of existence of a particle within a small box. So basically it's the probability, not the wave function, but rather the wave function, the absolute value of the wave function square is the probability density of finding a particle in a bounded box of infinite small dimensions. So that's what a wave function is, for us at least. And since it's a function, it means that you can define a space of these wave functions, and you can basically span this space with a basis set, like you would do in any other linear algebra, course or whatever. So the only difference is that normally in linear algebra we are dealing with discrete system, vectors, matrices. Here we are dealing with a continuous system. So it's a function, and then there are other functions that are the members of a basis set. When you linearly combine those members, you can basically make each and every wave function that exists. So ideally. But normally practical wave function basis sets are not really and mathematically basis sets. So that's important to know. And again, you have all of the features of a basis set. So if you have a basis set to span the space of wave functions, then those basis sets could be orthonormal, which basically means that if you multiply that a member of that basis set by its conjugate transport and integrate, you should get 1. And if you do the same thing with any other basis member of the set, you should get 0, which is what this delta function is. The other thing that I want to mention is this thing called the Hamiltonian operator, which allows you to compute the energy of your system. So a Hamiltonian operator is basically the sum of energy of all of the particles that are in your system. So all of these particles, they have kinetic and potential energy. So for instance, the first one in this Hamiltonian definition is the energy of kinetic energy of electrons. The next one is the kinetic energy of nuclei, and then you have the potential energy, which is the nuclei electron attraction force, and then electron repulsion forces, and then nuclei repulsion. And when you perform this operator on your wave function, you are going to get the energy. So what the second equation in this slide shows is an eigenvalue equation, essentially, where you are performing this Hamiltonian operator on your wave function, and you're getting an energy. Now, what is important here is that there is a certain wave function for which you are going to get the ground state energy, or the minimum energy possible for the system. Next thing to know is the approximations that people have come about to make things easier. One of these approximations is the Born-Oppenheimer approximation, which basically allows you to rid yourself of the nuclear part of this Hamiltonian. The underlying assumption is that since electrons are tinier and their mass is much less than, like 3 orders of magnitude less than a proton, they basically move much faster than the nuclei. Therefore, while the electronic system is relaxing or settling down to its ground state, or any state for that matter, you can assume that during that time the nuclei hasn't moved at all. So that basically means that you can take out the nuclear part and just solve for the electronic part, and then use the electronic part to solve the nuclear part. Which, in other words, to make it short and nice and easy, it means that the nuclear part of the Hamiltonian of the wave function is independent of the electronic part, which is what this last equation is showing. And in other words, if you just find the energy of the electrons, or the energy of the system per electrons, the electronic energy, you can simply add the nuclear repulsion up to that, and then get the total energy. So you don't have to find everything, assuming that the nuclei is also a wave and moves and stuff like that. You just assume that they are charged particles that are not moving. Okay, knowing that, so we have to talk about how the wave function is built. The wave function is basically, as I mentioned, this entity that shows the whereabouts of these electrons probabilistically. And it has some certain features that physicists have come up with. And one of these features is that a wave function has to be antisymmetric. And by that, I mean if you change the location of 2 electrons, the value of this wave function should become negative. So the reason behind these has to do with the Pauli exclusion principle and the fact that these are fermions, and the other fact is that they have to be indistinguishable. As in, one electron, it should not be really different than the other electron in the system. You shouldn't be able to tell them apart. So all of these impose these characteristics on us. And the other thing that I want to mention is that one very easy way of coming up with with the total electronic wave function is to basically assume that the total electronic wave function is the multiplication of all of these single electron wave functions. So for electron 1, you have psi 1. For electron 2, you have psi 2. For electron 3, you have psi 3. And so psi 1 multiplied by psi 2 multiplied by psi 3 all the way to psi n should be your electronic wave function. However, the problem is that such a wave function would not satisfy the antisymmetric property. Now, in order to make it satisfy the antisymmetric property, there are lots of ways you can make that happen. One of these ways is to use a Slater determinant, which is this determinant that we have in this slide. This guarantees that you will have indistinguishability. And now, what we're talking about here are the single electron wave functions as the indices of this determinant. And you have, of course, n of them, but this determinant is n by n. Therefore, as you can see, you are basically putting the all of the electrons in all of the wave functions. So if you have n electrons and n wave functions, this determinant, the first column is basically all of the wave functions when you put the electron 1 in them. The second column is all of the wave functions when you put the second electron, and so on and so forth. So, for example, imagine if we are dealing with the helium atom, which has 2 electrons and therefore 2 wave functions. Both of them are in the s orbital. One of them is s spin up, the other one is s spin down. So let's just call them phi1 and phi2. So as you can see, the first column is phi1, r1, and r2. Well, I did the opposite of what I just told you, so which doesn't matter in terms of determinant. So let's look at the column here. Phi1, r1, and then phi2, r1, which basically means the first the electron 1 in wave function 1 and electron 1 in wave function 2, and then the second row, which is electron 2 in wave function 1 and then electron 2 in wave function 2. And then you perform this determinant, you are going to see that it's 1 over square root of, well, this. Now, you can check for yourselves that this is indeed antisymmetric. I replaced the R1 and R2, the 2 electrons, and what I get here is the negative of the above. So it is antisymmetric. And if we were to assume that these phi1 and phi2, each of them were normal as well, normalized, which means that let me go back quickly. If we assume that those were normal, which means that integral of phi1, well, there should be a conjugate transpose sign here. Phi1 conjugate transpose phi1 conjugate transpose dr would have been 1. If that was the case, then you can also check that this total wave function is also normalized. So that's one thing. And there is one small thing that I want to get your attention to, and that is, I just told you that both of these are the same s orbital, and the only thing that differs is the spin, which basically means that phi1 and phi2 from the perspective of r are the same thing. So they're spatially the same. And if we didn't have the spin part, which we kind of cannot show here, I guess we could, but you cannot really write it down because it's not a function of space, then phi1 and phi2 would have been the same if we didn't have the spin. And therefore, this determinant would become 0. And this is important for us because when we are dealing with numerical simulations, we cannot have the spin being taken care of within the computer. And therefore, if we were to just use a Slater determinant like this Slater determinant would become 0. So I'll tell you later how we actually take care of that. Now that we have our wave function, so that psi being the Slater determinant, and I've also mentioned that h psi equals some e psi. Now, if we want to actually find what E is, we can look at this equation, the first equation, and multiply it from the left-hand side by a psi. Now, this is a notation that I did not introduce, but what it means is that instead of writing down all of those integrals, we are just going to use this notation. So just to quickly remind you what that is, or if you haven't come across it, which by now I think you have, these are called bra and ket. So this one, which is basically ket psi multiplied by bra psi, is essentially that integral of psi conjugate transpose multiplied by psi integrated over r. So that's what it is. Now, the interesting thing is that this is going to be an e within a number within an integral. So a number multiplied by one of the integrants can just come out. And so you're going to have e multiplied by that integral. Whereas on this side, h is an operator, so it cannot come out. Imagine if it's like sine of theta or something. It cannot just come out of the integral. So it remains within the integral. So this one would be an integral like what you see in the last line here. It would be psi conjugate transpose multiplied by h multiplied by psi and integrated over all of the spatial dimensions of all of the electrons. So that's what it is. Now, assuming that we perform this, then E would be this guy divided by the integral of psi conjugate transpose psi. One question that you might ask yourselves is that then we say that psi is essentially orthonormal, or rather normalized. And if that's the case, then this guy should become 1, this psi conjugate transpose psi integrated. Well, yes, but we don't know if it's normalized, and we don't want to impose that condition, so we go by a more general form, because the wave function that we might make up in order to get the results may not be normalized. Maybe we didn't normalize it. So let's just go by the most general condition and show that it in fact doesn't have to be normalized. It could just satisfy. E can be found with this equation easily. Now that we have the equation to find the energy, we need to, how do we find the ground state energy? Well, we are going to use this thing called the variational principle, or rather the variational theorem, which basically says that there is one wave function that gives you the ground state energy, and any other wave function gives you an energy which is bigger than the ground state energy. You can easily prove that. And if that's the case, then we can simply keep, well, not simply, but we can keep changing the wave function in the hopes of getting a smaller e than our current e value. And as we get a smaller and smaller e's, we are going to get to a point that we can, we are either in a minimum of this e, or we are not in a minimum, but we think we are in a minimum, and we just assume that this is the ground state energy, and that wave function that we found is the ground state wave function. Now, again, one little thing that I have to mention is that we can basically have a wave function that is parametrized and then change those parameters such that we minimize this value of E. And then the minimum value of E is our ground state energy, and the parameters or the wave function based on which we achieve that ground state energy is our ground state wave function. Now, how does that relate to Monte Carlo? Well, in order to, so not for the minimization, but just to calculate this energy, you actually have to perform these two integrals that I mentioned. So this integral on top and this integral on the bottom. And this alone is a tough task, and that's exactly where we are using the Monte Carlo method, so this is not the variational part, this is just the Monte Carlo. Variation comes from varying these parameters, set of parameters, let's say set of alpha, which gives us the minimum energy, while performing Monte Carlo integrals on here to calculate the energy per set of parameters. So how do we calculate this energy? We use the good old Monte Carlo method that by now, again, you should be familiar with. It's used everywhere in finance and minimizations and anything that is not a straightforward convex optimization. It was shown that Monte Carlo is probably one of the effective solutions. So in order to change this E equation into a form that is Monte Carlo-able, or rather that is something that we can perform a metropolis condition on, we just add psi multiplied by 1 over psi right in the middle here, as you can see. And so now we have two pieces. So this is essentially one, but we have now two pieces. One piece is looks like a probability distribution, and you can easily see that it's a probability distribution. So it's the square root of, it's a absolute value of psi r squared divided by psi r squared over integrated over the whole space. Now, if you look at it, it's basically the value divided by the sum of all of the possible values. So it's a distribution multiplied by this 1 over r h, 1 over psi r h psi r. And this thing we call local energy. It has nothing to do with anything physical. So it's not an actual physical energy. We just call it local because it changes with r. So it's localized per r. We call this local energy. And what we are doing essentially from now on is just to perform a Monte Carlo into a weighted integration where Monte Carlo comes in, because this weight is basically a probability distribution, this rho r, that we are actually going to perform Monte Carlo on. So the way it works is basically the Metropolis algorithm, and the Metropolis algorithm, you can actually check it in Wikipedia. The way it works is that you start from some r, let's call it r0 for the iteration 0, and then you change this r by generating random r's, and then performing this condition test. So if rho rn divided by rho rn minus 1, so it's between iteration n minus 1 and iteration n, is bigger than a random number that you generate right there, then you accept a move from rn minus 1 to rn. So then that means that in your sum, integral sum, you're going to add rho rn multiplied by elrn. If this condition is not satisfied, then you reject that sample rn, and instead you just add another rn minus 1, which means rho rn minus 1 multiplied by elrn minus 1. And you keep doing that until you reach a condition. Condition normally is that until adding these up to your E no longer changes the value of E, or it basically has damped to a value, and that means that you've reached the you've converged to your integral. Or on the other hand, you could have another condition like saying that after 1 billion iteration, just stop it. Okay, so now that we know how everything works, I want to get back to how we actually form the variational wave function. So That was the Monte Carlo part, and here is now the variational part. I already told you that you're going to use a Slater determinant. Now, as I told you, Slater determinant is just one way of making this wave function satisfy all of those anti-symmetric property and whatnot. There are other ways, but at the same time, this Slater determinant is also an approximation of the actual wave function, and it does not satisfy certain conditions about these wave functions that I don't want to get into. In order to make it satisfy those conditions better, we actually multiply it with another thing, which is called the Jastrow-Peday, I think, functions. So this Jastrow-Peday functions, per each pair of electrons, you just compute this thing, where A is 2 if these are for parallel spins. So if electron I and electron J are both a spin up or both a spin down, A is 2. And if one of them is a spin up, the other one is spin down, it's 4. Beta, however, is something that you are actually, it's one of your variational parameters, one of those that you're computing. So as you can see here, it's a multiplicative sum of all of those Jijs. So it's not just one Jij, it's per all of the pairs of electrons, you compute a Jij and multiply it to this guy. If you remember, I also mentioned that this guy is going to be 0 unless if you have somehow considered the spin into these wave functions. Now, I also said that you cannot consider the spins into these wave functions because this spatial, we don't have a suitable definition of a spin, and it's not related to spatial parameters. So we cannot really put it in our computer program. So what do we do instead? Well, there are articles out there where they prove that instead of using this Slater determinant, you can use this other determinant, which approximates the actual determinant, which is basically a Slater determinant for all of the spin up electrons multiplied by another Slater determinant, which is for all of the spin down electrons. The problem here is that this is no longer anti-symmetric. And anti-symmetry was the condition we needed to satisfy based on which we actually built this Slater determinant. But it doesn't matter, because with VMC, at least in this case, we are not that concerned about finding the right wave function, but rather finding the right energy. And what those papers that I mentioned prove is that this Slater determinant is good enough for computing the energy. So it gives you the right energy, although this is not the right wave function. Now, so we took care of the spin problem. And so what people simply do is that if you have n electrons, you just assume half of them are spin up, the other half is spin down. And you do the determinant for each of these sets separately and multiply them together. One other thing that I want to mention is that each of these single electron wave functions is an LCA, or linear combination of atomic orbitals. Linear combination of atomic orbitals means that you have orbitals on each atom, you add them up together, and or not all of them, maybe some of them, and then you basically have the molecular orbital. So for psi1, for electron 1, you can assume that electron 1 is probably just going to be on atom 1, let's say. So you just add up all of the orbitals of atom 1 with some weights for the electron 1. And so your variational parameters in this case are going to be this, what do you call it? Alpha ij here. So this is going to be, these alphas along with these betas are going to be your variational parameters, those that you vary and you get new wave functions, and then you perform the Monte Carlo algorithm and find the energy, and again you change these parameters with a new wave function, and so on and so forth. So all boils down to an algorithm that looks like this. this Monte Carlo part, the MC part, is this big box with the green flowchart, and the variational part are all of these boxes outside here. So you change the alphas and betas, you make a new and basically do all of the multiplications and Slater determinants, you make a new wave function. Then you go through the Monte Carlo part that I just explained with a condition, and then you find an energy, and then you update your parameters. Hopefully you will get to a lower energy. And you perform this until, so for this one you can perform like gradient descent, other methods, or it could also be a randomized method. This part itself could be a Monte Carlo method as well. And finally, you're going to have a set of parameters that give you the ground state energy or something very close to it. One thing that I need to mention is this metropolis part. If you see here, I'm just dividing the psi rn square by psi rn minus 1 square. Whereas here, I was talking about phi rn and phi rn minus 1. So I'm basically canceling this integral at the bottom, because when you're dividing the two, this integral is over all of the r's and it doesn't change. So it's going to be the same, and so you can get rid of it. And so that wraps up what I wanted to present for today. I am going to hopefully make another one of these when I make my own competing solution to what you guys will be building. Not that we are competing, but rather the two paths that we are taking. Thank you. And these sources, by the way, are very good and help me a lot. Thank you. Goodbye.